Thanks, Mina, for that lovely introduction, and welcome to my talk, Fantastic Front-End Performance Tricks and Why We Do Them. So as Mina mentioned, I'm a front-end engineer at Slack. I work on search and autocomplete. I spend a lot of time thinking about the quick switcher. Feel free to tweet questions, comments, and compliments at me at my Twitter handle, which is Zeigen Vector. I'll also be around after for the rest of the conference if you want to talk to me then. All right, so this talk is going to be a whirlwind tour of front-end performance. We're going to talk about a lot of things. It's going to be information-packed because there are just so many things that you can do to help with front-end performance. So again, a lot of tips and tricks, some more advanced and complicated than others, but all rooted in the way that networks and browsers work, and humans work, actually. So for me, these tips really start to pop when you understand why we're doing them. So I'll be sure to sprinkle that context in along the way. So the goal of front-end performance from the user's perspective is twofold. One, we want to get them the information that they need as soon as possible. So I'll be talking about some tricks for loading performance. We also want to ensure that our users are going to have a smooth experience interacting with the website. So I'll also talk about some render performance tricks. On the loading side, we want to make sure that we are loading everything as quickly as possible, so we're going to want to keep things small. We're also going to want to keep things smart, which I'll go into what that means when I get there. And from the rendering side, we want to keep things smooth. But before I really dig in, I'm going to do a super quick overview of how the browser gets the information from the server and turns it into a website. Because again, this context really makes these tricks shine, and when you really start to understand why we're doing them, they start to make a lot more sense. So this is the minimum amount of information I can give you to really get a sense of why we're doing things, but Katie and others will go into more about how browsers work, so then this will all really start to fall into place. So first, a bit about packets and protocols. For those not familiar, a packet is a unit of data sent over a network, like, say, the internet, that contains a payload of information. Protocols are the ways that these entities, like computers, transmit information among them over these networks. TCP, or the Transport Control Protocol, is the protocol that underlies HTTP, or the Hypertext Transfer Protocol, which powers the internet. It uses packets to send information from one computer to another. TCP's job is to deliver a reliable, ordered, and error-checked stream of packets across the network from one computer to another. TCP also has congestion control. So these requests are going to start small, and they're going to ramp up in size to make sure that the network can support the requests. This is going to help the computers send things at exactly the right speed based on each other's bandwidth and the health of the network itself. So at this point, the browser and the server have established their TCP connection. In practice, because most of us are still living in an HTTP 1.1 world, this is going to be up to 6 connections. Because the browser knows it has a lot of work to do, it kind of wants to get ahead of it, so it's going to open a bunch of them. The browser is going to then get all the information that it needs to build a web page by sending an HTTP request to the server. The server will then send over the HTML document. As the browser parses the HTML, it will likely come across references to other things like CSS, JavaScript, images, and it's going to need to send off requests to the server to get those things too. So the HTML is going to get parsed and turned into a structure called the DOM, or the Document Object Model. Likewise, the CSS is going to get parsed and turned into a structure called the CSS-OM, or CSS Object Model. And then by their powers combined, we get a render tree, which is then used to do the layout and painting of the elements on the screen. So the idea here is that we want to create a render tree as soon as possible, and the process by which we do this is by optimizing the critical rendering path. So one thing that you can do to do this is to keep things small. In general, we want to be sending as few packets as possible because that means sending all the information to the user as soon as possible. Though the total size of your website should not be your end-all be-all performance metric. One of the first things you should do in this is minifying your HTML, CSS, and JavaScript. Minification is the process of removing all the unnecessary characters from your source code without changing its functionality. So we're talking things like white space, comments, new line characters, which are all used to add readability to your code, but your computer doesn't really care about them. They're not really used for execution at all. So while it's super important to make sure that these things are in your code for when other humans are reading them and when you're writing your code, when it's time to pass it off to the computer, we want to get rid of it. And a tool for doing this is Uglify. So here's a really toy example so you can see what's going on. This is unminified code of 4 lines, readable. This is minified code, 1 line, less readable, just to give you a sense. Another thing that you can do is compressing your HTML, CSS, and JavaScript. Gzip is a really popular compression method for web things. Gzip, I saw a talk a few years ago, and this just stuck with me. It replaces repeated substrings with references to where the decompressor can find that substring elsewhere in the document, and then it's going to go through and take that output and try and represent it in as few bytes as possible. So if you think about an HTML document, how many times the string div appears in there, you start to get a sense of how good this could potentially be. In fact, gzipping generally reduces the response size by about 70%. So a real-life example, you can see here the gzipped and non-gzipped versions. In that far right column, we have numbers like 43.4 versus 176. So you can see this is really great for HTML, CSS, and JavaScript. We are getting those 70% numbers, but not great for images. But there is some optimization that you can do for images, and it is also really important because JPEGs and PNGs can be really big, especially for mobile, and SVGs generally have some extra information in them put in by Sketch or Illustrator, as well as white space, because SVGs are also markup. So running these images through an optimizer such as Vigo or a tiny PNG or a tiny JPEG can remove the extra information. You should also gzip your SVGs because, again, also markup. So for instance, say you want to take this here chonk chart from being a mega chonker to a fine boy. We can then pass it through tiny PNG and it becomes a fine boy indeed with 47% savings. Amazing. Something you're also going to want to do is make sure that you're using the right type of image, right image type for what your image actually is. So for example, vector graphics, like SVGs, are really good for, are really all the rage these days, as Sarah Drasner's talk is going to show you why. But they are best for simple geometric illustrations like line drawings, while raster images like JPEGs and PNGs are best for photographs. You also might want to look into responsive image options, such as a souped up image tag with your source set and sizes attributes, or the picture element, or even WebP if you're feeling super fancy. Caching is also something that really helps with performance across the board, across the web request response lifecycle, but let's focus on how we can use it to continue to download as few things as possible. So in general, resources should be cacheable for either a very short amount of time if they're going to change a bunch, or indefinitely if they are static. And then in this case, you can even use fingerprinting, which is when you have a very, very specific URL for a specific version of a file, which then changes when the contents change. This, combined with the header cache control immutable, is gaining popularity. Caching helps with performance because you don't need to send things that are already on your computer. 0 bytes is very small indeed. So something else you might want to do is carefully consider the impact of libraries and frameworks, both for site size and for developer productivity, because we don't want to forget that we are writing code for humans and we are humans. But if you do need a framework, which is perfectly cool, make sure you choose carefully. You might want to look into the total cost of the size and the initial parse times before choosing an option. On a smaller scale, a lot of libraries have split what was previously a monolith into discrete modules. So right now, thinking about Lodash, because it's likely that you're not using every single module that it has to offer. So this gives you the opportunity to import only what you're using instead of the entire library. Also consider if the browsers that you're looking to support can do these things natively, and if you really don't need to import like map from Lodash. And Ryan will talk more about the effects of third-party libraries on performance in his talk. In a more advanced realm, tree shaking might also be a good way to reduce the size of the files that you're sending over the wire. Tree shaking is done by module bundlers like Webpack and Rollup, and they rely on the import and export statements to detect if modules are going to end up getting used and include only that code in the bundle. Fonts, often really big. Can you get away with using UI system fonts? Maybe. That would be cool. If you can't, that's also cool, but chances are that the web fonts that you're using have a lot of stuff in there that you aren't using, like glyphs and extra weights and extra features. There's a bunch of stuff that can probably be done with fonts. I don't know much about it, but Mandy's talk later is all about fonts, so there might be some good stuff in there for you. Putting files on a CDN means that these files are as close to your end user as possible, which is going to keep the round trip time small. So despite the speed of light being, fast, it's actually a limiting factor in getting packets from you to your user. So CDNs are great for reducing that round trip time. All right, keeping things smart. And by smart, I mean think about the order that you're loading things. I probably should have called this unblocked, but unblocked doesn't start with sm, so here we are. So one of the first things you should think about doing in this department is combining your files together. So concatenate your CSS together and concatenate your JavaScript together, not in the same file. You want to do this using, you can do this using a tool like Webpack or Rollup or even the asset pipeline. This might end up coming back to bite you with caching, because over time, if you change just one file in your bundle, the whole cache gets invalidated, but that's not a reason to not do this. You might just want to have 2 bundles for each of these languages, one for application code that's likely to change a bunch, and one for vendor code that is less likely to change. Along this realm, you might want to consider using Css Sprites or icon fonts so there aren't so many small little images, each with their own requests, but also be aware that this can backfire if the sprite sheet gets too large. So why are we smushing all these files together, right? It's not necessarily making there be any fewer bytes. So remember how we opened 6 TCP connections at the beginning? That's how many parallel downloads you can do at once in HTTP 1.1. So, and even those 6 parallel downloads is a hack around the spec. So this is a huge bottleneck, so a bunch of these optimizations are trying to get around this. Another one in this realm is domain sharding, which is serving your images from multiple hostnames or subdomains to, again, get around the hostname parallel download limit. One of the most classic performance techniques in the Smart department is putting your scripts at the bottom of the page, right before the closing body tag. This is because the HTML parser is doing its parsing, and when it runs into a JavaScript include, further parsing is going to stop. And this is because JavaScript has the ability to manipulate the DOM using document.write, so then any HTML that might get added must be fed back into the main parser. So parsing of the HTML document is going to stop until the scripts are downloaded, if they're not already downloaded, and executed. And when the script is downloading, the browser won't start any other downloads, even on different host names. There are also some more spec-approved ways to get around this blocking too. You could add a defer attribute, which will cause the document to not halt document parsing and will execute only after HTML is parsed. You can also mark the script as async, which will be, so it will be parsed and executed in a different thread in parallel. With this, you're kind of promising that you won't call document.write, or if you do, that you're okay with it getting thrown out the window, which is a DOM pun. Okay. So here's an example: defer, async, easy, cool. Now for some more advanced moves. If you're using a bundler like Webpack or Rollup, you can also take advantage of code splitting. This feature is going to split your code into chunks, which then can get loaded asynchronously on demand. So therefore, not all of your JavaScript and CSS has to be downloaded, parsed, and compiled right away. You could even go a step further with this, with more expensive scripts, and load them asynchronously right when they're needed with the Intersection Observer API. This provides a way to see if part of your page that needs this code is within the viewport, and if it is, then you can execute a callback, which could be loading a script. On the other hand, CSS is supposed to go at the top of the HTML document in the head tag. So remember that CSS is required for building the render tree because the CSS SOM is half of the information for it. So you're going to want to kick off this request as soon as possible so that you can download the CSS and have it there ready. Putting style sheets at the bottom of the document prohibits progressive rendering in a lot of browsers. So this is going to block rendering and so that the browser can avoid having to redraw all the elements on the page. So from a user experience perspective, you're doing this to avoid that flash of unstyled content. However, some people who are really trying to juice their performance might subvert this and inline critical CSS in the head of the document and put the rest a little bit later. Critical CSS is the minimum blocking set of CSS that we need to make the page appear to a user. The idea here is that we should prioritize everything we need to get the above the fold content there and ready, and you want to do this within the first few TCP packets, which at the early phase of TCP is going to be around 14K. So this is really high rolling stuff. So by inlining the CSS, you're going to be cutting out the time that you otherwise need to do the round trip and get the styles. But also, it is a little challenging to figure out what exactly are those critical styles. So again, this is super advanced stuff, but good to know. HTTP2. So Patrick will dig into this much more tomorrow, but it's a new HTTP spec that serves to fix a bunch of the aspects of HTTP 1.1 that we need to optimize around all the time. So once this is implemented, a bunch of the optimizations I just discussed will be obsolete, which is cool. I'm glad they're going to help us out. We don't have to do all this stuff. But loading performance is only half of the story. We want to be keeping things smooth for our users. So while some of these tricks that we discussed are one and done, it's your Webpack configuration. If you have a front-end infrastructure team, they might do that for you. These are things that you should be thinking about as a day-to-day as a front-end engineer as you're writing code. These are things that really going to help you try and really make things smooth as you're developing them across the site. So let's pick up the story of what's going on in your browser. So when we last left our heroes, we were combining the DOM and the CSS DOM into a render tree. So while the render tree contains all this information about what nodes are visible and computed styles are there, we haven't yet figured out where all these things are going or how big they're supposed to be, and this is all part of the layout process. Once we know the location and dimensions of these things, we can then start to represent them on the page, which is the painting phase. This process is going to make layers from the bottom up, creating a bitmap for each layer, and then these bitmaps are going to get handed to the GPU for compositing, or more technically, smushing all the layers together. So this whole thing can occur at about 60 frames per second, actually not at 60 frames per second, or about every 16.66 milliseconds. But this is under super perfect conditions. So the brain scientist in me can't help tell you this juicy detail. 60 hertz, 60 frames per second, also happens to be the frame rate of the central human visual field, so isn't that lucky? I don't think it's a coincidence. Also, on a much less mechanical level, our minds, in an attempt to kind of reconcile all these human-made things with the laws of nature, take choppy, discrete inputs, like a flipbook or something that's being re-rendered a bunch of times per second, and make a seamless experience out of it that we perceive as continuous motion. This is called apparent motion. So just to recap, getting the pixels to appear on the screen happens in three main phases: layout, painting, and compositing. The 60 frames per second, I said, only happens under perfect conditions. For as you see, renders are constrained by the speed of your JavaScript. We haven't talked at all about what happens with JavaScript in the browser, but JavaScript is single-threaded, running on the browser's main thread, along with all the style, layout, and painting calculations. So everything that gets called in JavaScript is going to go onto the stack. Synchronous calls go right on, and async callbacks, like those from the web APIs, are going to get thrown into a callback queue and are able to be moved onto the main stack by the event loop once that stack is cleared. There's also a render queue that tries to get renders done that 60 times per second, but renders can't happen if there's anything on the JavaScript call stack. That's why nothing can render when you are in an infinite loop, because the call stays on the stack, preventing renders from getting initiated. And Chibi will talk more about the complexities of all of the scheduling in her talk. So I hope that detour will help put the rest of these things I have to say into perspective. Now back to your regularly scheduled performance tips. So something that I found particularly useful lately is using debouncing or throttling in inputs. My work these days is a lot of, with autocomplete, it's a lot of computationally intensive filtering and sorting based on users typing a query into an input. So debouncing or throttling this call, so the searching happens once only, say, every 100 milliseconds, instead of on every keystroke, has drastically improved performance. It was amazing. So Lodash has handy debounce and throttle functions, so include just them, and you can just wrap that function that you want to debounce in that function, and you are set. If you're affecting visual changes with JavaScript, you are going to want to do this just the right time, and there's a special debouncing just for that. So wrapping your updating function in window.requestAnimationFrame is going to ask the browser to call your function just before the next repaint. And this is particularly great for scroll handlers and other things that affect visual changes based on user input. This is important because if the timing of updating where the pixels are on the screen is not in sync with when the repaints are happening, then you might just drop frames and your users won't get that continuous motion, and they'll see jank or lag. Luckily, a lot of the frameworks that we use, like React, have this baked in for you, so you don't have to worry about it. But if you're going vanilla, like I did on my personal website, where this code snippet is pulled right from, you might need to use it. So on my website, I'd wanted to be cute and draw SVG triangles on the bottom that filled up the entire width of the screen. So when I asked a friend to review it, the first thing he did was make the screen go narrow and wide really quickly, and it's like getting you of a performance problem. So I wrapped the updating call in window.requestAnimationFrame, and that was all the magic I needed. So if you're doing computationally intensive stuff with JavaScript that isn't pushing pixels around, chances are that you could move it to a web worker, which is kind of a more advanced tip here. So web workers are a way for you to run JavaScript in background threads. And they're pretty versatile, but they do have some limitations. You don't have access to the DOM, so you can't do any DOM manipulation with them. They also don't have access to some things that live on the window object, but they have access to other stuff, like the cache, WebSockets, XML HTTP requests, and more. And we've been exploring using web workers at Slack for some of our performance needs. As I mentioned, any JavaScript computations that go on the browser's main thread need to complete within 16 milliseconds to ensure an unblocked next paint. So moving things that might take longer off the main thread that you can, so they aren't gumming up the crucial call stack, is going to allow all this stuff to run more smoothly. Now for some CSS things. If you need to animate something, you might want to use transform or opacity as opposed to example position or display. While the latter are great for one-and-done positioning, they're not good for animation. Detour to give you an example of what I'm talking about. So you see in this keyframes you have top and left. Better choice would be this transform translate. So why do we want to do this? Because transform and opacity can be handled by the compositor alone. So compositing is that last post-paint step, and it doesn't require a relayout or a repaint, which are expensive. Another thing that you might want to do is reduce CSS selector complexity. And using a CSS methodology is one way that you can help do this by controlling selector nesting. So the deeper that styles go, the longer it's going to take for the browser to figure out if there's a match. So many of these proper methodologies rely on giving each element a name that is pretty strictly defined. So it's easy for the browser to figure out if a rule should be applied or not because these things have classes instead of these huge selector strings in your CSS files. So I've become partial to BEM, which stands for Block Element Modifier, because we use it at Slack, but there's also a bunch of other methodologies like SmackSuit and Object-Oriented CSS. So for example, this is pre-methodology, we have this selector, which is asking, is this an element with the class of title, which has a parent who happens to be the negative nth child plus 1 element with the class of box. That's a lot for a human and for a browser. So figuring this out has the potential to be pretty time consuming, as the browser has to go and gain a lot of information about the element and its siblings. This is a lot easier for both the human and browser. So that's BAM. Okay, so this all being said, I'm going to give a caveat and say that you shouldn't do any optimization until you know that you need to optimize. Learning how to assess performance could and should be a talk in and of itself, and there's a lot of resources that exist out there. But here's a super minified version of what you can do just in Chrome. So you have tools like the network, performance, and memory panels, and Chrome's Lighthouse in the audit tab for doing synthetic testing right on your browser. So synthetic testing is only half of the performance story, because it's only going to give you insight into how your site is doing under controlled conditions, even if that controlled condition is simulating slow 3G in the network panel. The other side of performance testing is real user testing. Here you can use the resource timing, user timing, and navigation timing APIs right there in your browser. So navigation timing is going to collect metrics for the document as a whole. Resource timing will collect information about your CSS files or JavaScript files, images, etc. And the user timing API allows you to measure how long bits of your code run for. And all of these, again, living right there on the window.performance object. And because they exist in most modern browsers, they can be used to gather metrics and beacon them back home for aggregation. And I couldn't help myself, I needed to include a slide about flame graphs because they've been a personal fave and very helpful for me lately as I tried to debug some stuff at work. Again, autocompletes can be very slow, but they need to be very fast because people expect instantaneous results, like in a lot of cases. So this tool has been invaluable for zeroing in on performance bottlenecks, like when we were sorting really big arrays of empty strings. Don't do that. Okay, so all this stuff is only the tip of the iceberg, so learn more about performance testing and performance tricks, implement them, and then make changes based on what your app and your users need. Things like code splitting and lazy loading are advanced and time-consuming, and you might be able to spend your time doing other things if your users don't actually need them and if they're not going to help you very much. All right, so that's the end. Remember to keep your things small, keep things smart, and keep things smooth. Here are some resources for a bunch of the things that I talked about, and here's all the songs that I butchered. All right, thank you for listening. Again, I'll be around after if you have any questions.